Hello children. Today I am going to continue with the numerical and conceptual problems of Biot-Savart law. So let us start with our first question. So what the first question says, as shown in figure, a cell is connected across points x and y. We are able to see a cell is connected across points x and y of a uniform circular conductor. Then you are going to prove that the magnetic field at its center will be 0. What about the magnetic field due to this setup at the center will be 0. Now can focus on the diagram. We are able to see there is a circular loop. What about the midpoint of the circular loop is O. Across the circular loop, a cell is connected across x and y, I can say. You know, at point x, the current splits. We are able to see very clearly. At point x, the current will split. I1 is the current flowing through the part XAY. I2 is the current flowing through the part XBY. So if this is the situation, you are going to prove that the magnetic field at the center will be 0. So let us start. So already we know what is magnetic field due to a circular loop, and also what is magnetic field due to angle subtended by a circular loop. All those formulas, I think it is very clear with you. So with that basic concepts, we can get into the solution. So we're able to see there are two parts of the loop. Say I'm going to assume one part, it is XAY. I'm going to assume it subtends an angle theta 1. I'm going to assume it subtends an angle theta 1. So what about the mathematical form? So what is magnetic field due to the part? Say it is XAY will be mu naught by 4 pi. I is I1 by A is the radius into, what about the angle subtended? I'm going to mark it as theta. The magnetic field due to the part XAY, I'm going to assume it subtends an angle theta 1. So what about the magnetic field expression can be written as mu naught by 4 pi I1 by A into theta 1. I'm going to mark it as equation number 1. Where it acts, I think by using the right rule, we're able to see the fingers are along the direction of flow of current. The thumb will indicate the direction of magnetic field. So you are able to see it is inwards. Where it acts inwards. Similarly, I'm going to write what about the contribution to the other part, that is XBY mu naught by 4 pi. What about the current flowing through this part is I2. The radius is A only. I am assuming it subtends an angle theta 2. It subtends an angle theta 2. Mark it as equation number 2. Once again you are able to see by using the rule, it acts outwards. Yes. Now our aim is to prove what is the magnetic field at the center to be 0. So if I am going to prove if they are equal and opposite, our aim will be achieved. So let us try to prove that. You know, since the two parts of the circular loop are connected across the same points of the cell, since the two parts of the circular loop are connected across the same points of the cell, the potential difference of these two parts will be equal. The potential difference across the two parts will be equal. So mathematically what I can write, I1 into, say R1 is the resistance of this part, is equal to I2 into R2. What is the logic behind this equation? Since the two parts of the loop are connected across the same points of the cell, the potential difference across the two parts will be same. So if I1 is the current and R1 is the resistance of the part XAY, should be equal to I2 is the current and the resistance of the part, say R2 for XBY. Now let us say what will be R1. You know, resistance can be written as, what about the length into unit resistance. Basically the formula for resistance I can use, what about the total length for which you want the resistance into unit resistance. So let us assume the unit resistance is R. I'm going to assume the unit resistance is R. What about the length of the part? You are able to see the length of the part is XAY. Obviously it's an arc. And you know, arc length is radius into theta. What about the arc length formula? It's a very basic formula you are using from smaller classes. What about arc length can be written as arc angle into radius. What is the radius? What I'm going to assume is the radius is A. What about the arc angle is theta 1 into R. Once again I'm going to repeat this. What about the resistance of XAY can be determined by multiplying the length of that part with the unit resistance. Multiplying the length of that part with the unit resistance. How to get the length? Obviously it's a arc length. What about arc length is radius into arc angle. Radius is A. What about the arc angle is theta 1. So that arc length can be replaced as A theta 1 into R. Similarly, so I'm going to mark it as R1. So what about R1? I can write I1 into A theta 1 into R. By using the same logic, I can use R2 as A theta 2 into R. What are the things that is going to be cancelled off? We're able to see A, R, they are going to be cancelled out. So what I'm going to get is I1 theta 1 is equal to I2 theta 2. Mark it as equation number 3. So obviously if I'm going to use this 3 in 1 and 2, what happens? Since they are equal and opposite, the net magnetic field at the center will be 0. So once again I'm going to read out the question. As shown in figure, a cell is connected across points X and Y of a uniform circular conductor. Prove that magnetic field at its center will be 0. So how we started? We assumed there are two parts of the circular loop. The first part subtends an angle theta 1. The second part subtends an angle theta 2. So what about the expression for magnetic field is mu naught by 4 pi I1 by A theta 1 for the part XAY. Similarly, what about the magnetic field for the part XBY will be mu naught by 4 pi I2 by A theta 2. Mark it as equation number 2. So what about the direction of the two magnetic fields? One is inward, other is outward. So by some means, if I am going to prove I1 theta 1 is equal to I2 theta 2, this means our aim is achieved. The magnetic field at the center will be 0. For that, what I am assuming, since the two parts of the circular loop are connected across XY, obviously the potential difference remains same. That is I1 R1 can be written as I2. I1 R1 is equal to I2 R2. So how to get the resistance? You know, resistance can be obtained by multiplying the length with the unit resistance. So what about the length? Say, what is the length of XAY is basically an arc. What about arc length is arc angle into radius. So L can be replaced by A theta 1. So R1 can be replaced as A theta 1 R. Similarly, R2 can be replaced as A theta 2 R. A and R are cancelling on both sides, and I'm going to arrive at I1 theta 1 is equal to I2 theta 2. If I'm going to use this in the 1 and 2 equation, I'm clearly getting the magnetic field at the center is 0. So with this, I'm going to get into the next question. My next question is, a student records the following data for the magnitudes of the magnetic field at axial points at different distances x from the center of a circular coil of radius A carrying a current I. Obviously, in a very simple language, it is the case of axial line of a circular loop. So you are going to verify for any two set of values that these observations are in good agreement with the expected theoretical values as shown in the table. So let us start. I'm going to prove for two sets. The remaining sets you can do as a home assignment. So let us get into the question. What the question says. What about the magnetic field at a point on the axial line? You know what is the magnetic field at a point on the axial line? You know is B is equal to mu naught by 4 pi 2 pi I A square by A square plus x square to the power 3 by 2. You know this is the basic formula for magnetic field at a point on the axis of a current carrying circular loop. So let us check for the first value. So what they are saying in the first value, they are setting x equal to 0. They are setting x equal to 0. So I'm going to set x equal to 0. Setting x equal to 0. What will happen? You are able to see B is equal to mu naught by 4 pi 2 pi I A square by, in place of A square is A square only, in place of x it is 0 to the power 3 by 2. So what will happen? It is mu naught by 4 pi 2 pi I A square by, you know, A square to the power 3 by 2, 2 cancels off, you may be getting A cube, and this is going to cancel. So what is the final reduced form is mu naught by 4 pi 2 pi I by A, and they are saying it to be taken as B naught. I'm going to assume this is the value at the center of a current carrying circular loop, and also you are very clear what is the formula for the center cases: mu naught by 4 pi 2 pi I by A, and I'm going to take this value as B naught. Now let us check the second set of value. So what is the second set? They are saying set x equal to A. They are saying put x is equal to A. In place of x you are going to put A, and you are going to prove this. It should be 0.25 root 2 times the initial value. You are going to prove this 0.25 root 2 times the initial value. So once again I am going to say B is equal to mu naught by 4 pi 2 pi I A square by A square, and in place of x also it is A square to the power 3 by 2. So what will be the reduction value? It is mu naught by 4 pi 2 pi I A square by, I'm going to simplify this part, A square can be taken out, so it will be A square to the power 3 by 2. What is the thing that is left is 1 plus 1 is 2, 2 to the power 3 by 2 can be written as root 2 cube, can be written as root 2 cube. So you can do the simplification. So you're able to see it is mu naught by 4 pi 2 pi I A square by, this 2 cancels off, so it will be A cube, and root 2 cube can be written as 2 root 2. Root 2 cube can be written as 2 root 2. This cube and A square will cancel off. So what is the left out value you are able to see? It is mu naught by 4 pi 2 pi I by A into 1 by 2 root 2. And I think if I am going to reduce 1 by 2 root 2, you are able to get it is 0.25 root 2 times the initial value. So once again our aim is to prove this value as per the data. Initially I am going to set x is equal to 0. What was the magnetic field is B naught. We proved that by setting x equal to 0. By putting x equal to 0 I am getting B is equal to mu naught by 4 pi 2 pi I by A, and I am going to mark it as B naught as per the question. Now my second data is you are going to set x equal to A. This means in place of x you are going to put A, and you are going to prove that this becomes 0.25 root 2 the initial value, that is 0.25 into root 2 B naught. So the simplification you are able to see very clearly. I am going to get at the last, it is 0.25 root 2 B naught. You are able to see in the question there are two other sets of value. One is x equal to 2A and another is x equal to 3A. You are going to take these two sets and you are going to prove whether the values are as per the table or not. So this type of question also creeps in board examination. Obviously it checks your application power of the formula. With this I'm going to get into my next question. Our question is, calculate the magnetic field at center O due to a current carrying conductor bent into a square of side A. Once again our aim is to calculate the magnetic field at center O due to a current carrying conductor bent into a square of side. Say what about the side given to you is A. So obviously this is also one of the application of Biot-Savart law. So I think the question is very simple. A straight current carrying wire is given to you. You are going to bend into a square. What about the side of the square is A? What will be the magnetic field at center O? You are going to calculate. So how the diagram becomes? You are able to see. So a wire is bent in the form of a square. So I am going to mark the edges A, B, C, D. Say O is the midpoint. O is the midpoint. What about the magnetic field when a current, say I flows? I'm going to say the current I flows as shown. Let us check first. What about the direction of magnetic field due to each side of the square? What about the side of the square? They are saying it is A. So you are able to use the right hand thumb rule. I'm going to use for the part AB. You are able to see the thumb indicates the direction of flow of current, and at point O it acts outwards. So for AB, since the current is flowing in this direction, what about the magnetic field is outwards. Similarly, you can check for all other parts. In each case, you are able to see the magnetic field is perpendicular to the plane and acts outwards. So just by getting the magnetic field contribution due to one side, I'm going to multiply it with 4 to get the total value. So I'm going to get, what about the magnetic field, say due to the edge AB. I'm going to multiply that value with 4 to get the total magnetic field. So what about the total magnetic field at the center will be 4 times the magnetic field due to the, say, the side AB. So you know, obviously, what is the type of figure you are able to recall? It is a straight conductor with point in the middle. You are able to see this point is in the middle. So I'm going to mark this as OD. I'm going to mark this as OD. Say, obviously you are able to see this will be 45 degree and this will be also 45 degree. Now, what about the formula for BAB? It is mu naught by 4 pi to, it is I by A, mu naught by 4 pi, I by A sine phi 1 plus sine phi 2. I think you can recall this formula for a finite length by putting the values. Mu naught by 4 pi, say it is I by, you are able to see this length becomes A by 2. If the total length is A, OD will be A by 2. So in place of A, I'm going to put A by 2, that 2 moves up. Once again, in place of A, I'm putting A by 2, that 2 moves up. And what about sine phi 1 is sine 45. Once again, sine phi 2 is also sine 45. Once again, it is mu naught by 4 pi 2 I by A. Sine 45 is 1 by root 2 plus 1 by root 2 is 2 by root 2. And what about the total magnetic field is 4 times this value, that is mu naught by 4 pi 2I by A into 2 by root 2. And do the simplification, are able to see this 4 cancels off. So what I'm going to get is B is equal to mu naught by pi I by A 4 by root 2, can do root 2 by root 2. So what will happen? It's mu naught by pi I by A, root 2 is 2, so that becomes 2, so I'm going to get it as 2 root 2. So what is the final formula for magnetic field at the center? When a wire is converted into a square as shown, the magnetic field will be mu naught I 2 root 2 by pi A. Once again, I'm going to repeat the question. We are supposed to calculate the magnetic field at center O due to a current carrying conductor bent into a square of side A. So how we started? I'm going to assume the square will be ABCD. What is the logic behind this question? What I said is, since it's a symmetrical figure, what about the direction of current through AB is outwards? Similar is the case for the other edges also, the other sides also. So what about the net magnetic field at O will be 4 times due to any one side of the square. So I'm going to get AB is my reference side. So I can assume the net magnetic field will be 4 times the magnetic field due to AB. So how to get AB? Obviously it is a straight conductor with a finite length. And what is the formula for straight conductor with a finite length is mu naught by 4 pi I by A sine phi 1 plus sine phi 2. You are very clear to see what about the angles are 45 and 45. By setting all the values, doing the simplification, what about the magnetic field at the center comes to be mu naught by pi I by A 2 root 2. My next question is, two insulating infinitely long wires are lying mutually perpendicular to each other as shown in figure. If the two wires carry currents I1 and I2 as shown in figure, find the magnetic field at point P with the coordinates A, B. So we're able to see in the diagram, there are two mutually perpendicular infinitely long straight conductors. That is, we're able to see the first conductor carries a current I1, the second conductor carries a current I2. Our aim is to find what is the magnetic field at this coordinate, say P, A, B. So let us explore one by one the contribution of each straight conductor at point P. So I'm going to take my first conductor, say the current I1. You apply the rule. You are able to see the current flows in the direction of thumb. At point P, it acts inwards. So what about the direction of magnetic field? Due to the flow of current I1, it acts inwards. So I'm going to mark it as B1. It will be, infinite case, mu naught by 4 pi 2I by A for infinite straight current carrying conductor, and if the point is in the middle, what about the magnetic field is mu naught by 4 pi 2I by A. So here B1 is mu naught by 4 pi 2, what about the current they are saying is I1, and what about the location distance is A, where it acts inwards. It acts inwards. Similarly, let us get into what about the direction of magnetic field due to the flow of current I2. We are able to check. The thumb indicates the direction of flow of current and the fingers gives the direction of magnetic field, and you are able to see it acts outwards. So what I can write as B2 is equal to mu naught by 4 pi 2I2 by B, and where it acts outwards. Now, magnitude wise you are able to see which will be greater. Since you are able to see the value of A is greater than B. Since A is greater than B, B2 is greater than B1. Since you are able to see they are reciprocally related, if A is greater than B, this means B2 should be greater than B1. So which will dominate? The B2 will dominate and our net field will act outward. So whether we are going to add the two values or subtract, obviously we are going to subtract the two values. So what about the net magnetic field will be mu naught by 4 pi into 2 can be taken common. What is left here is 1 by B. What is left in the first one is 1 by A. Can do the simplification, it comes to B. So what is the net magnetic field? B is equal to mu naught by 2 pi 1 by B minus 1 by A, where it acts outwards. It acts outwards. So once again what the question says, two insulating infinitely long wires are lying mutually perpendicular to each other as shown in figure. If the two wires carry currents I1 and I2 as shown in figure, find the magnetic field at point P with the coordinates A, B. How we started? We started from the first conductor carrying current I1. It's an infinite case. What is the formula for an infinite straight current carrying conductor? When point P is in the middle, it is mu naught by 4 pi 2I by A. So how the equation modifies for the first one? B1 is equal to mu naught by 4 pi 2I1 by A. By applying the direction rule, it acts inwards. Number 2, what about the current I2? It creates a magnetic field B2, mu naught by 4 pi 2I2 by B. What about the direction? Outwards. Since the diagram says A is greater than B, by the diagram I am getting, since A is greater than B, so the magnitude of B2 should be greater than B1. So the net value will be the subtracted value, that is B2 minus B1. So what are the things that is at the last I am going to get is B is equal to mu naught by 2 pi 1 by B minus 1 by A, and where it acts outward. Similar is a question you can get into the next one. It is a similar question what we did now. What the question says, two insulating infinite long wires are lying mutually perpendicular to each other as shown. Two insulating infinitely long wires are lying mutually perpendicular to each other as shown in figure. If the two wires carry currents I1 and I2, if the two wires carry current I1 and I2 as shown in figure, find the locus of the point. You are supposed to find the locus of the point where the magnetic field due to two wire is 0. So I'm going to read the question once again. Two insulating infinitely long wires are lying mutually perpendicular to each other as shown. If two wires carrying currents I1 and I2, find the locus of the point where the magnetic field due to the two wires is 0. So obviously it is somewhat similar to what we did in the last question. So you're going to assume a point, say P, say the coordinates are x comma y, I can keep x comma y. Obviously it will be the x value and it will be the y value. You are going to get the coordinate values for the value to magnetic field at P should be 0. So how we started? What is magnetic field due to the first part? Mu naught by 4 pi 2 I1 by, what about the distance is x. What about the magnetic field due to the second part is mu naught by 4 pi 2 I2 by y. Since what they are asking, what is the net magnetic field at a coordinate is 0, obviously they should be equal and opposite in direction and magnitude. So I'm going to equate the two sets. What are the things that is going to be cancelled? I think you can clearly guess. Mu naught by 4 pi cancels. It's 2 cancels. So what I'm getting is I1y is equal to I2x. Yeah, y is equal to I2 by I1 into x. So what the question says, you are going to find the locus of the point where the magnetic field due to the two wires is 0. So what is the basic assumption? At that point, the magnetic field due to the two conductors should be equal and opposite. Due to the two conductors should be equal and opposite. So what I'm using is B1 is equal to B2. Magnitude wise, they should be equal. Already in the last question we proved one is inward, other is outward. So direction wise the things are set. Only we are going to say that the magnitudes are equal. So I'm setting the magnitudes to be equal and I'm getting y is equal to I2 by I1 into x. So with this, I'm going to end my session. Take care of yourself.